Yeah. Now we are going to talk about the training of this GAN structure. We have the generator, discriminator. So we have the theta G as well as the theta D to train, so that we are going to make the generator as good as possible to produce some good samples to through the discriminator, and the discriminator is going to train itself such that it is possible to tell whether it is the sample that is from the real samples or from the fixed sample. So in order to perform the training, we have to set up the cost objective or the loss function. Yeah, so we use the cost entropy. If you look into the literature, we have more than this cost function. Yeah, but this function that is from the first paper. Yeah, from Ian Goodfellow. Yeah, so if you would like to have more information, and then just go to take a look at the paper. But this is the cost function we have. That is what we are going to optimize, which consists of two parts. The first part, that is, we call this is for the real samples. We are going to draw X from the distribution of the real data. That is right here, and then compute the cost entropy. Yeah, so log dx. This dx, that is, when we feed in X in real sample X into the discriminator, we collect dx right here. Yeah, so X, that is from the real sample. The next one, that is, we draw Z from this distribution BZ, that is the latent, and generate GZ, and then feed it into the discriminator and collect dx. So this is the fixed samples, and then put it into the discriminator, collect right here. So 1 minus this one and take the log. So this one, that is for the fixed sample. Okay, just to remind that this E as well as this E right here, that is the expectation operator. Yeah, refer to this link if you do not know what it is. Yeah, so we are going to compute the expectance of the information right here. And there are two remarks right here. When we use the log, actually it refers to the lateral log, that is the log with the base exponential. Yeah, or the lateral log. Yeah, so when we look at this bit as well as this one, it is not necessary to use the whole data set for the training, and then so we can use the mini batch. Yeah, we will see that in the pseudocode of the training. That means we are going to draw some samples from the training data set to calculate the expectance of this bit as well as this one. And now, once we have this cost function defined, we are going to make sense of it to understand why we set up the cost function like this. Okay, and now when we do the training, we call this as a minimax game. Yeah, because we are not just simply maximize or minimize this function. We are going to do maximization and minimization. Maximize this with respect to D. That means we are going to maximize this cost function subject to theta D, that is with respect to the discriminator. And then, so that is our comment right here. And then we are going to minimize that is with respect to G, with respect to the generator. That means we are going to adjust the parameters of the generator in order to minimize the cost V. Okay, so what we are going to do, that is, first we are going to maximize the theta G, maximize V by adjusting theta D. That is the first step. Do it a few times if you wish, or you can do it one time. After that, we are going to minimize V by adjusting theta G. That is what we are going to do in the pseudocode. Yeah. And now we try to understand the physical meaning of this cost function. First, we take a look at the lateral log. Now this is the lateral log property. So we divide into a number of segments. That is, when A, so this is the x-axis, that is A. When A, that is 0. So this one, that is 0. When A, that is 1, this point, that is 1. Feed it into this knot. the y value, it would be 0 right here. If the a value that is in this range 0 to 1, we will just find out that the log value, that is y, will be in the range of 0 to 1. So closer to, when a is closer to 0, and then when a is closer to 0, and then the y value is closer to minus infinity. When a is closer to 1, and then the y value that is closer to 0, that is about this portion, yeah? Okay, when a that is 0, that is this point. So y value will be minus infinity. So that means when we talk about the y value that is not a in the range of 0 to 1, it is all negative except this point, the maximum value that is 0, yeah? Okay, and now we are going to talk about the training objective again. So we would like to maximize the chance to recognize the real sample when the sample is real, and generated when the sample that is from the generator, and then the discriminator will tell it is fake. That means when the real sample x that is from here, and then the discriminator will give you 1. When x that is from the generator, the discriminator will give you 0, yeah? So this is what we want the discriminator is going to do. For the generator right here, we would like to, through the discriminator, that means when we generate gz right here, input it into the discriminator, we expect that dx would be 1, because the generator's output is real enough in that case, yeah? Okay, and now take a look at this one. We are going to train the discriminator. Train the discriminator when g that is fixed. That means we are going to fix theta g. Now we are going to fix theta g, that is theta g right here. We are going to adjust theta g so that we are going to maximize the cost. Take a look at this bit first. This is the expected value of log dx. This dx, this x that is drawn from the real distribution. That is, we are talking about the real samples. So in that case, we need to think about what we expect the output of dx would be. That is right here. So when we fit in the real sample into this x, and then so what we want to collect in this dx, that is, because this is the real sample from the discriminator point of view, we want this to be 1, because we would like the dx to tell that this sample that is from the real sample, yeah? Okay, so gz, okay, we are going to take a look at this generator. What kind of thing we want it to be, yeah? Because at the moment, I think that we do not have a what value it is, because this gz, that is a sample. If we would like to generate an image, that would be just an image. We do not have any expectation, but from the data distribution point of view, we would like to have the data distribution is the same as the real sample distribution. Okay, and now take a look at this one. That is this term. We are talking about log dx, x that is from the real sample. According to this log characteristic, when dx that is 1, we come up with 0. That means we would like to have log d from the first expectation, that is 0. And then what about this one? Think about that. Now, from the discriminator point of view, we would like to tell that if the sample gz that is from the generator, that means the sample that is a fixed sample, we would like to have dgz to be 0. Okay. So 1 minus 0, that is 1. So not 1, which will give you, so when the input, that is 1, that is this point, it will give you 0. So combining these two information, that is, we would like to maximize this this one will become 0, this one will become 0. The meaning of the first term, this becomes 0. That means the discriminator can tell you that the sample, that is a real sample. And then so when we take a look at the second expectation, when this term becomes 0, that means the discriminator can tell you that the sample, that is from the generator. Yeah, so that's why we are going to maximize these two expectants, because the first one, that is to help the discriminator recognize better for real sample, as well as to recognize better for the generated sample in the second term. Yeah, and now we are going to, this is the reason why when we train the discriminator, why we have to maximize this cost. Now we are going to talk about the training of the generator. Yeah, we are going to talk about the training of the generator by adjusting theta g. Yeah, by adjusting theta g. So now we are going to minimize the same cost, but how come we do not have the first term? It is mainly because that when we adjust theta g, you can look at the first term that we do not have the generator. Yeah, we only have d. So that means the first term does not depend on theta g. We only have the second term. This is somewhat related to theta g. So we can consider this to be a constant and ignore that. Yeah, so that means if you're going to include that into this function, it doesn't matter, but we will waste the power of the computation. Yeah, so anyway, we are going to ignore the first term, and now we are going to ask the same question, but ask the same 4 questions from the point of view of the generator. Yeah, okay, from the point of view of the generator. So we are going to minimize the cost by adjusting theta g, and then so we would like to ask what value of dx it should be, or we expect that to be. Yeah, actually, if you look at this expectation, it does not relate to dx, so we don't care about what value dx it is. Yeah, so that's why we do not care about log dx as well. So what we care about, that is this term gz. Gz, again, this is a sample, say an image, a face. So we do not know what kind of information it is, but we care about dgz. That means when we fit in this fake face into this discriminator, and then we would like to know what value of this d it is. Yeah, so because the generator would like to generate the sample as real as possible. Yeah, so we expect that when we do the generator, this dgx would be 1, because we can through the discriminator, the sample is real enough. Yeah, okay, so when d, that is 1 right here, so 1 minus 1, it becomes not 0. When this input is 0, from this figure we will know that it approach minus infinity. Yeah, so it will approach minus infinity. So that's why we are going to minimize the when we adjust the theta g. Yeah, because when it approaches infinity, it means that the generated sample, that is real enough to through the discriminator. Yeah, so in this slide we understand the physical meaning, the actual meaning, why we are going to do the maximization of v with respect to d, as well as minimization of v with respect to g. Now we are going to take a look at the overall picture. How do we do the training? Yeah, this is the pseudocode. So we have a for loop at the top. This for loop, that is the number of training iteration. That means we are going to determine how many times we are going to train the discriminator as well as the generator. Yeah. So this one, that is for the discriminator, and then this one, that is for the generator. We are going to choose a constant value, constant integer k. That is, we are going to update the parameter of theta d by k times. Yeah. Before doing that, we are going to do the mini batch. That is to generate z1 to zm. That is, we have m this z value, and then we will have m of the gz. Yeah. So that means we are going to generate m fixed samples as a mini batch for the training. Yeah, for the training of the discriminator. Now, right here, we also need to prepare a mini batch. Yeah, so we are going to draw m samples from the real samples. Yeah, so we have m here, m fixed samples. We have here in total 2 m samples. Feed it into the discriminator. So we are going to compute the gradients using this equation. Now this equation, this sign right here, that is the gradient. Yeah, because we used the stochastic gradient approach. That means we are going to find the gradient. Now when we are going to repeat this loop a few times, for example, when we get to this point, we come up with the alpha. Yeah, so we have the alpha value, that is the gradient of this bit, and then to update theta d. So we have theta d plus, not plus, the current theta d plus eta d. This is the learning rate greater than 0, and then plus this times this alpha. Yeah, so that is what we have done in the neural network. We apply the gradient descent update rule. Yeah, because we are going to do the maximization. So this sign is plus instead of minus. Yeah, so through this loop, we are able to update theta d, and then now get to the second point. After we update the discriminator parameters, we are going to update the generator parameters. We do the same thing. Draw m samples. So that means we are going to have m gz fixed samples, and then update the generator by descending its stochastic gradient, because we are going to do minimization. Yeah. So assume that this is beta equals this gradient of this bit. That is the entropy we talk about in order to update theta g. So we do the updated theta g, that is from the current theta g plus eta g, that is the learning weight greater than 0 times beta. Sorry, this one should be minus. Yeah, because we do minimization. Yeah. Okay. So to remind that when we calculate this gradient, we are going to use the theta d value at this point. That is the theta d value before the update. Yeah. So that is so right here, that is we use this value and then compute theta g. So again, the first for loop, that is for how many update we are going to do for the discriminator and generator. In this block, that is for maximizing this cost function. In this block, that is to minimize this by adjusting the value of theta g. Yeah, the generator. This is for discriminator. This is for the generator. Okay, to put it in a diagram, that is, we have this GAN structure. Here, this is the GAN structure in the training. And then here, that is, we are going to prepare the samples X and Z and then compute the expectance using this formula, using this cost. Once we find the gradient right here, we are going to compute this value. Once we compute this value, this is alpha, we are going to update the theta g using the current value of theta g plus the learning rate times alpha. And then so this is what we do in this block. And then in this block, we are going to use some mini batch to compute this beta value. And then we are going to update the theta g, the generator parameters, by using the current value of theta g minus the learning rate, eta g times beta. Remember that this is minus because we do minimization. Yeah.